This video reviews the fundamental counting principle and also goes over the probability review in Canvas. The fundamental counting principle helps us to figure out the total number of outcomes in a probability experiment. So here's an example. A student is to roll a die, a number cube, and flip a coin. How many possible outcomes will there be? Well, each number on the die, the number cube, 1, 2, 3, 4, 5, 6, can be paired up with heads and it can be paired up with tails. So we can see the sample space, or the total number of outcomes, is 12. The fundamental counting principle tells us we can take the outcomes of the first part of the experiment, so in this case rolling the die, there are 6 different outcomes, and multiply it by the outcomes of the second part of that experiment. In this case, flipping the coin has 2 outcomes to get a total of 12 outcomes. Let's look at another example. This is a rock, paper, scissors tree diagram. So player 1, we talked about this, has an option of choosing rock, paper, and scissors, and then player 2 has those same 3 options. And then we can see the outcomes for each game. We could figure out the total number of outcomes by making this tree diagram, and we can see we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Or we could have used the fundamental counting principle to say player 1 for each round has a total of 3 options, and player 2 has a total of 3 options, the rock, paper, scissors, to get 9 total outcomes. Here's another example. If you go to a restaurant and you have some choices, you can figure out the total number of combinations or the outcomes. So if we had 3 options for a sandwich, so chicken salad, turkey, or grilled cheese, we have 3. And then we have 3 options for a side, chips, french fries, or a fruit cup. So we multiply by 3 for that. And then 2 options for a drink. We multiply by 2. And so we could list out our tree diagram as you see to find the total number of combinations, or we can use the fundamental counting principle as a shortcut. And we would do 3 times 3 is 9, 9 times 2 is 18. Another example, so if you're at a restaurant and you have 3 sandwich choices, 2 soup choices, and 4 beverage choices, again we can multiply those different outcomes for each and get the total possible outcome. So in this case, 3 times 2 is 6, 6 times 4 is 24. All right, let's see if we can calculate this one. So a fast food restaurant has a special combo meal. Each bundle has a drink, a side meal, and a dessert. Here are the choices: lemon juice, coconut juice, cola, water. So in that, we have 4 options for a drink: pizza, hamburger, fries, or hot dog. 4 options. And then we have chocolate cake, ice cream, apple pie. So we have 3 options. So in this case, to find the total number of outcomes, I could list them all in a tree diagram, or I can use the fundamental counting principle and multiply these 3 numbers. So 4 times 4 is 16. 16 times 3 is 48. There are 48 possible combinations. How about if you go to McDonald's and get a Happy Meal? How many combinations do you think you have? So if you choose a meal, we can see here there's 1, 2, 3, 4, 5 options in this case. And so we would take 5. And then choosing a side, 1, 2, there's 2 options. And then 3 drinks. So to figure out our sample space or total number of outcomes, instead of drawing a tree diagram, we can use this counting principle. 5 times 2 is 10. 10 times 3 is 30. Lots of decisions to make. All right, let's look at the review assignment, the probability review assignment that's posted in Canvas. How many unique possible outcomes are there when flipping 3 coins? You could make a list to help you determine, or we can use that fundamental counting principle. And so you can see the list is started, pretending we have a penny, a nickel, and dime. Here are our outcomes, or we can go ahead and use that fundamental counting principle. So if we think about our first coin, it's a penny, and there are two possible outcomes, heads or tails. And then we have a nickel. There are two possible outcomes, heads or tails. And then we have a dime, two possible outcomes, heads or tails. So we can figure out the total number of outcomes using the fundamental counting principle, or we can continue that list. So I have 2 times 2 is 4, 4 times 2 is 8. 8 possible outcomes. Suppose a person flips one coin and then spins the spinner shown below. How many total possible outcomes are there? So again, I have 2 options. I can use the counting principle, or I can make a list. Maybe I'll make a list in this time, and then check with that counting principle. So I know my coin has heads or tails, and then the spinner is red, orange, or purple, and they're all equal sections. So I could spin red with heads, red with tails, orange with heads, orange with tails, or purple with heads and purple with tails. So there are 6 possible outcomes. I could also check using that fundamental counting principle on their spinner. There are 3 options. With the coin, there are 2 possibilities. So 3 times 2 equals 6 outcomes. Suppose you have a fair number cube with the numbers 1 through 6. What is the probability of rolling a 5 written as a fraction in simplest form? So when we're going to write the probability as a fraction, and in this case we're writing the probability of a 5, on the bottom is the total number of outcomes possible. So in this case, if we have a fair number cube, there are 6 numbers that can be rolled. And then I need to see how many how many 5s are there out of that 6 possibilities. And so I can see on a regular number cube, there's only 1 5 out of the 6 outcomes, and so the probability is 1/6. Suppose you have a fair number cube with the numbers 1 through 6. What is the probability of rolling an odd number written as a fraction in simplest form? Again, I have a total of, if I want to get the probability of an odd, I'm going to put the total options on a number cube or die, and that is 6. I can roll 1, 2, 3, 4, 5, or 6. But I want to figure out the probability of rolling an odd, so that would be 1, 3, or 5. So there are 3 out of 6 numbers that are odd. If you look at the options for my answer, though, 3, 6 is not an option. So I have to look back at that direction that says in simplest form. So 3, 6 is the same as 1/2. Question 5. Suppose you spin the spinner shown in the picture. What is the probability of landing on the 2 written as a %? So this time, I can see that I have 5 options. They all have the same size. There's only 1 2 on the spinner. So when I write that, only one section has a 2. So that's 1/5. But I want to write it as a %, and so I know % means per 100. So I'm going to change and write an equivalent fraction out of 100. So 5 times 20 equals 100. So 1 times 20 equals 20. So 20 out of 100 means 20%. Mario rolled a fair number cube 36 times. How many times should he expect to roll a 3? Well, first I'm just going to write the probability of rolling a 3. So again, I'm going to put the total possibilities. So on a number cube, there are 6 possibilities, and only 1 option for a 3. So the possibility of rolling a 3, or the probability of rolling a 3 is 1/6. If I want to figure out what's the probability or what he should expect if he rolls 36 times, I'm going to write an equivalent fraction that shows 36 times. Because the first one says, if I roll 6 times, I should expect to roll a 3 1 time. But this time, I'm rolling 36 times. So I'm going to think, 6 times what gets me to 36? 6. And so 1 times 6, he should expect to roll it 6 times. The table shows the results of a spinner experiment. Find the experimental probability of spinning a 4. Choose 2 ways that represent the probability of spinning a 4. So first thing I need to do is total the number of spins. And so I'm going to go to that occurrences. That's how many trials happened in this experiment. And I'm going to add that up. So when I add 6 plus 11 plus 19 plus 14, I get 50 total trials. So then I'm going to go and write the probability of spinning a 4. And so out of the 50 spins, 4 was rolled 14 times. Now I look at my options and I don't see 14/50ths, and so that tells me I should simplify. So I'm going to divide by the greatest common factor of these two numbers, which is 2, and I get 7/25. Nope, I see that as an option, but I know I have to find 2. So I can't simplify 7/25 anymore, so these other fractions are not going to be an option. So I have to figure out what is the percent that's equivalent to 7/25. And so I'm going to write an equivalent fraction or ratio to show out of 100, so I can get percent. So 25 times 4 equals 100, so 7 times 4 equals 28. So 28 out of 100 would mean 28%. So that is the other correct answer.